Rutherford Backscattering Spectrometry, RBS, by Michael Durso, Justin Edberg, Sarah Galvin, Chris Gregory, Devin Hardy, and Elias Sugarman.
Rutherford Backscattering Spectroscopy, or RBS, is named after Sir Ernest Rutherford, 1st Baron Rutherford of Nelson, OMFRS. Rutherford was a prominent physicist of the late 19th and early 20th centuries with major contributions in the fields of particle and radiation physics. RBS bears his name because the spectroscopy technique is based on the discovery that alpha particles elastically backscatter off the nucleus of the atom, disproving the Thomson or plum pudding model. While Rutherford's experiment was designed to fire ionized helium particles in air at a gold film, modern RBS systems are substantially more complex. RBS is a method of determining the composition and thickness of samples in the absence of standards. It relies on the elastic collision of hard sphere incidence and target particles. It is used for near-surface layer analysis of solids and has the additional benefit of being quantitative without requiring reference samples. The data acquired can be used to produce estimations of thin film structures, like the copper-silver-silicon structure of a thin film transistor. The RBS system used here at ASU has a two-stage accelerator that utilizes the application of high voltage to helium plasma as a source of helium plus ions and rubidium as a converter element that produced helium minus ions. Nitrogen is also used in the accelerator as a stripper element to convert helium minus ions into helium plus plus ions. Upon passing through the terminal and being exposed to the nitrogen, the helium ions become heavily positively charged due to the charge exchange principles and are repelled by the positive terminal. This accelerates the ions up to energies exceeding 2 mega electron volts that are then directed at the surface sample. The collision of the ions with the sample produce backscattered particles which are then picked up and analyzed by various detectors. The Tandetron acceleration tubes are constructed by sandwiching titanium electrodes between glass insulating rings. The electrodes have a central hole which allows the ion beam to pass through several cutouts and hold magnets to suppress secondary electrons. The assembled tube structure evenly distributes an applied potential by resistive grating, which connects a resistor change across each electrode and smoothly distributes the total voltage from terminal to ground. The uniform electric field needed for acceleration is produced only inside the acceleration tube and not at the entrance or exits of the tubes. The effect of a non-uniform field is to cause unwanted beam focusing, particularly for particles with low energies, effectively filtering them out. A gas stripping region located in the terminal housing removes electrons from high-energy particles. The negative ions from the low-energy acceleration tube lose electrons in the stripper and become positive so that they are accelerated a second time down the high-energy acceleration tube. Gas stripping is used in the Tandetron for good reliability and consists of a dilute target of gas atoms in a long, thin tube. In order to maintain the high potentials and potential gradients inside the Tandetron, special attention must be paid to proper electrical insulation. Electrical insulation in the Tandetron is of three types: gaseous, solid, and vacuum. The electrical insulation must have sufficient dielectric strength and be properly shielded to prevent locally high stresses and surface tracking. Gaseous insulation in the Tandetron is sulfur hexafluoride, a heavy non-toxic insulating material with a dielectric strength of approximately 2.5 to 3 times the dielectric strength of air. The apparently large safety margins are necessary to compensate for the impurities in the sulfur hexafluoride, such as air and water vapor, and to compensate for local stress intensification. The solid insulation in the Tandetron consists of the glass insulators in the acceleration tubes. Vacuum insulation is used inside the acceleration tubes and in the high-energy extension of the Tandetron. When vacuum is electrically stressed, the materials in the vacuum chamber undergo a process called conditioning. Conditioning consists of field-dependent currents, the magnitude of which depends on the condition of the cathode surface. Tarnished, water vapor covered, or microscopically rough surfaces produce a much higher conditioning current than clean surfaces. High currents can cause breakdown, so care must be taken to ensure that all surfaces are clean and smooth.
The recoiling particle energies required to calculate the mass of the atoms in a sample are measured with a solid-state detector. This consists of a single crystal of p-type silicon or germanium with a much thinner n-type layer on the face. The n-type region is positively biased, creating a depletion region between the n and p-type semiconductors. An incident alpha particle creates electrons and holes on impact in the depletion region. The more energy a particle has, the more electrons are freed. Due to the positive bias, the electrons travel to the n-type region where they create a voltage pulse, which is amplified, digitized, and scaled to correspond to the correct energy.
Once RBS has been done on a sample, we have to analyze the data. RBS analysis is done through a process of simulation, where we use a computer program to produce artificial data, and then change the parameters to most closely fit the data that was produced in the RBS spectrum. So I'm going to show you an example of that. I'm opening up a raw RBS file in RUMP, which is a simulation program. I'm going to put the simulation program on the left, and the data on the right. That's our raw spectrum indicated in black. I'm going to establish some environmental parameters. 10. And then we're ready to begin our simulation. So I'm going to enter simulation mode by indicating sim, S-I-M, and I'm going to start to build up my material in layers. Of simulation layer 1, we believe that this sample is made up of copper oxide on the top, copper silver in the middle, and then silicon substrate on the bottom. So our top layer is going to be a copper oxide. We're going to indicate composition CO, copper Cu, 60%, oxygen 40%. Now we also need to indicate a thickness for this layer. So we're going to indicate simulation layer 1, thickness of 550 per centimeter squared. Alright, there we go. Sometimes RUMP's a little finicky. So simulation layer 1, thickness 550 per centimeter squared. Now the per centimeter squared identifier is just used as a thickness value that's independent of bulk density. So that's what we're using for the simulation, but you could also do the simulation in angstroms. To show this layer, we're going to put sim show. There we go, we've built up our first layer. And now we just keep going. I've already done the simulation, so I know approximately what it should look like. I'm just going to try and push through it. We're going to indicate simulation layer 2, composition, copper 20% Ag 80, with a thickness of 1700 per centimeter squared. Layer 3, with a composition of copper 13 G87, and a thickness of 2700 per centimeter squared. And then finally a layer 4 for the substrate with a composition of silicon 1 and a thickness that's arbitrary because there's no way our RBS penetrated through to the base layer. We're just going to put it at 9,000. That's going to be our simulation. Now let's try and plot it. By plotting PL1, number 1 indicates our simulation layer, over 0, which is the layer of original data. Boop, there we go. And from there, we just manipulate some of the environmental parameters and things like thickness in our layers to try and fit the data better. So I'm going to try 6.2. There we go. And see, we're just going to keep getting better as we go. But that is the basics of how to conduct a simulation.
So now we know that Ernest Rutherford pioneered the ideas behind RBS, that he didn't like statistics and he didn't want to collect stamps. As to RBS itself, we learned that it uses a process to strip and accelerate ions through large potential fields and then shoot them at the sample. The ions then strike the sample and backscatter atoms from the surface that are picked up and analyzed by detectors. We can then take the raw data and simulate it to get all kinds of useful information about the sample. That's all, folks. Thanks for watching.